Hi, everyone. So now we're going to talk about a number which you can attach to any element of a group, which is called the order of that element. It's a basic invariant, and it tells you what number you have to raise that element of the group to get the identity element. So if you have to square the element to get to the identity, then it has order 2. If you have to cube it to get to the identity, then it has order 3, and so on. And so we're going to introduce this invariant and look at some of its basic properties. We are going to need to use some results from number theory related to the Euclidean algorithm in this section. And in the notes, I've included a link to a discussion of the Euclidean algorithm that you might find helpful to review before or maybe after you try to figure out what's going on here. Okay, so let's start with the definition. Suppose that we have a group G and we have an element little g in it. Then by definition, the order of that element little g is the number of elements in the cyclic subgroup that it generates, assuming that number is finite. If it's infinite, then we say that the order of g is infinity. And we write absolute value signs to give us the order of g in G. So let's look at some examples. For case of infinite order, let's just take the group to be Z, and let's take 2 to be our element. And if we look at the cyclic subgroup generated by 2, it's all multiples of 2. It's the set of even numbers. And there are infinitely many elements in that set. So here I'm using absolute value to mean the number of elements in a set, but we shorthand that to say that the order of 2 is infinite in integers. And in fact, the order of 1 is infinite, the order of 5 is infinite. The order of any g in G is going to be infinite, in the integers is going to be infinite, because when you take the subgroup that it generates, it's going to have infinitely many elements. Okay, let's look at some finite examples. Let's take G to be Z12. If we take 2 in G, then the subgroup that 2 generates consists of 2, 4, 6, 8, 10, and then 12, which is 0, and then it goes around again, 2, 4, 6, 8, 10, 0, 2. So that's all there is in the subgroup that it generates. And there are 1, 2, 3, 4, 5, 6 elements in there. So the order of 2 is 6. If we take 3 generates 3, 6, 9, and then 12, which is 0, and then it goes around and around and around, 3, 6, 9, 0, 3, 6, 9, 0. That's why we call these things cyclic. And therefore the order of 3 is 4. And we could look at 5 in G. The cyclic subgroup generated by 5 consists of 5, 10, 15, which is 3, 8, 13, which is 1, 6, 11, 16, which is 4, 9, 14, which is 2, 7, and then finally 12, which is back to 0. And if you count these up, you see there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 elements in there, so the order of 5 is 12. And in fact, 5 generates Z12 because the subgroup that it generates, if you have a subset of a set which has the same number of elements as the set, then they're equal. So the fact that the order of 5 is 12 is equivalent to saying that 5 generates Z12. We could maybe look at one other example. Suppose we take the quaternion group, which has plus or minus 1, plus or minus I, plus or minus j, and plus or minus k in it. What's the order of I? Well, the cyclic subgroup generated by I has elements I squared, which is minus 1, I cubed, which is minus I, and I to the fourth, which is 1. So the cyclic subgroup generated by I has 4 elements, So the order of I is 4. And so is the order of j, and so is the order of k, and so is the order of minus I, minus j, and minus k. What about minus 1? If you take the subgroup generated by minus 1, it contains minus 1 and 1, because it goes minus 1, and then you square it, you get 1, you square it, you cube it, you get minus 1, fourth power, you get 1, and so on. And so the order of minus 1 is 2. None of these elements have order 8, so this quaternion group isn't cyclic. It's not generated by one element. So now let's prove a few theorems about orders of elements. So the first theorem we're going to prove is that if G is cyclic of order n and generated by A, so in other words, if G is equal to the subgroup generated by A, or more generally, we would say that if A has order n, A is an element of an arbitrary group and it has order n, then that's equivalent. The powers of A which give back the identity element are exactly the multiples of n. In other words, A to the k is equal to the identity element if and only if n divides k. And to prove this theorem, we're going to start out by characterizing the order a little bit differently. Instead of saying that it's the order of this group, we're going to show that, first of all, that the order of A in G is the smallest positive n such that A to the n equals E, or it's infinity if no such n exists. So if A to the n is never equal to E, then the cyclic subgroup generated by A is going to contain A squared, A cubed, and so forth. Let's consider that case first. Suppose A to the n is not E for all n. Well, let's look at A squared, A cubed, and so forth. These are all different. Because if A to the I equaled A to the j, for some I different from j, then A to the I minus j would be equal to the identity. We could multiply both sides of this equation by A to the minus j, and we would get A to the I minus j equals the identity, and therefore we would have an n in Z with A to the n equal to the identity. It might happen that this n were negative, but we can always arrange it. I mean, also A to the minus n is also equal to E, so we can assume n is positive by choosing A to the I minus j or A to the j minus I. So A has infinite order if and only if A to the n is never equal to E. A has finite order if A to the n is equal to E eventually, for some n. So A has finite order there has to be, if A has finite order, there has to be some power for which you get the identity. Otherwise, it would have infinite order. That's what we showed in the previous case. So we can choose the smallest n so that n is bigger than 0 and A to the n is equal to the identity. And I claim that that's the order. And to see that, let's look at A to the 0, A to the 1, A to the 2, and so forth out to A to the n minus 1. So clearly, this is contained in the cyclic subgroup generated by A, because these are all powers of A. But it's also the case, I claim, that they're actually equal, because if A to the K, let's take A to the K for any K, we can write this as, given A to the K, write K equals some multiple of N plus a remainder with R bigger than or equal to 0 and less than N. And then A to the K is equal to A to the Sn plus R. But A to the N is equal to the identity, so this is equal to A to the N to the S times A to the R, which is equal to the identity times A to the R. And R is bigger than or equal to 0 and strictly less than N, so therefore A to the K is in this set. So every power of A is in that set. So this is precisely A. There's only one other thing which could go wrong, what if two of these things were equal? But that can't happen either, because suppose two of them were equal. Suppose A to the I equals A to the J, where I and J are both between 0 and n minus 1. Well, that would mean that let's assume that I is bigger than J, just for simplicity. Then, the J is bigger than I. Then A to the J minus I would be equal to the identity. But J minus I, since these both are numbers between 0 and n minus 1, their difference is also between 0 and n minus 1. It's a positive number. And this would give us a positive number smaller than n. And A to the J minus I would equal E. And the only way that can happen is if J minus I is 0. So these n elements are all different, and they cover all the powers of A. And so we conclude, therefore, that the order of A is n, because we see that the cyclic subgroup generated by A has n elements. But we also have the final result, because let's go back to our thing we're trying to prove. So if A to the K, if n divides K, then A to the N is A to the T, A to the K, is A to the T times N for some T, which is A to the N to the T, which is the identity element. So if n divides K, then A to the K is equal to E. And on the other hand, if we just proved if A to the K is equal to E, then we can write K equals Sn plus R, where R is between 0 and n, and we would get that A to the K is A to the Sn plus R, which is A to the N to the S times A to the R. A to the N is the identity element. So that's equal to A to the R, which is the identity. But here we have R less than N and bigger than or equal to 0. And N is the smallest positive integer for which A to the R can be equal to E. So since R is less than N, R must equal 0. And that tells us that K is a multiple of N. So what we've shown here is that the order of an element is the smallest positive integer n, so that A to the n is equal to the identity element. It's also the order of the cyclic subgroup that A generates. And if A to the K is the identity, then K must be a multiple of n. So you have to, if you want to think about it in terms of cycles, if you go around, if a to the k is 0, that means that when you go around the cycle of the group k times, you come back to the identity, you must have done a complete cycle a certain number of times. So a complete cycle means n r times. Now, let's prove something a little bit even stronger than that. Let's suppose that we have a cyclic group of order n and we have a generator of it, A. And let's suppose that we take a power, B equals A to the K. And we can ask, what is the order? If the order of A is n, what is the order of A to the K? And this is an interesting question. Even if you go way back to our example of Z12, remember that in Z12, the order of 1 is 12. The order of 2, however, is 6. The order of 3 is 4. And in the context of this result here, if G were Z12, and A was 1, which is a generator of Z12, and B is 3 times 1, so K equals 3. Remember that here we're writing the group law additively. So instead of writing 1 cubed, we really mean 1 plus 1 plus 1, not 1. So that's important to keep track of. In the case of Z12, we write addition instead of multiplication. So we don't mean 1 cubed, 1 times 1 times 1. We mean 1 plus 1 plus 1. Because the operation, raising to the k power means do the operation k times. And here the operation is addition. And the order of 3 we worked out was 4. And what the proposition gives us is a formula. It says that the order of B should be n over d, where d is the greatest common divisor of k and n. So in this example here, k is 3, n is 12. The GCD of k and n is the GCD of 3 and 12, which is 3. And so the order is supposed to be 12 over 3, which is 4, which checks out. And maybe we could look at one other. Remember, we worked out the case where k was 5. So that was the case of the group generated by 5, which is 5 times 1. And in that case, the GCD of 5 and 12 is 1. And so the order of 5 is supposed to be 12 over 1, which is 12. And that does also check out in our calculation that we did way back here. We found that the order of 5 was 12. And if you want, you can also check for 2. The GCD of 2 and 12 is 6. Sorry, the GCD of 2 and 12 is 2, and 12 over that GCD is 6, and that's the order of 2. So this is seems to be a believable formula. To prove it, we need to use a little bit more number theory. So I need a little lemma, which says that suppose n, k, and r are integers, and suppose that n divides k times r. Then if d is another integer, and d divides n and d divides k, then n over d divides k over d times r. So what is this saying? To say that n divides k times r is to say that to say that n divides k times r is to say that kr is some multiple y times n. To say that d divides n is to say that n is a times d, and k is b times d. That's what it means to have d divides k. So if we plug all that in, we get B dr equals YAD. And if we cancel the d's, we get that dr equals YA. But A is N over D, and B is K over D. So this does in fact tell us that K over dr, this should be a B. K over dr is a multiple of N over D. And that's what the little lemma says. So that's the first lemma that we need. And the second lemma that we need says that if N divides KR and D is the greatest common divisor of K and N, then N over D divides R. So this maybe it helps to think about it a little bit. So for instance, if you have 6 divides 4 times 3, N is 6, K is 4, R is 3. The greatest common divisor, D, is the greatest common divisor of 6 and 4, which is 2. Then if you divide this equation out by 2 using the previous result, you would get that 3 divides 2 times 3. And we divided out the greatest common divisor of these two numbers from both of them, so now they have no factors in common. So the only way what's left can divide this product is if it divides the other number. And in fact, that's true here because 3 does divide 3. And this is where we finally have to use the Euclidean algorithm. So the proof here is that we write the greatest common divisor of K and N as a linear combination of K and N using Euclidean algorithm. So by Euclid, we have xk plus yn equals d. And therefore, we know that d is the greatest common divisor of both K and N, so it divides K and N. So we can factor it out. So we have x times K over D plus y times N over D equals 1. And then we multiply that by R, and we get x times K over dr plus y times N over dr equals R. And notice that N over D divides this, and N over D divides K over dr, because remember that N divides KR, and D divides N and D divides K, so N over D divides K over D times R. That's the previous lemma. But if N over D divides this and N over D divides this, then N over D divides that, so N over D divides R. And now we can finally work out the theorem that we're trying to prove, because what do we have? We have B is A to the K, and we want to know what is remember the order of B is the smallest power so that B to the M is the identity. And if we look at A to the Km equals the identity, by our previous result, this happens only if N divides Km. And we want the smallest power of M so that N divides Km. But N divides Km by the previous result means that N over D has to divide M. And so the smallest choice we can make is M equals N over D. And that tells us that the order of B is n over d. N over d is the smallest thing we can multiply k by, so that k times n over d is a multiple of n. And a corollary of this is that we have a generator R of Zn if and only if it's relatively prime to n, or more generally, if you have a cyclic group generated by G, then G to the R is a generator if and only if the power R is relatively prime. It has no factors in common with n, which is the order. And we saw this for Z12. The generators for Z12 are 1, not 2 because 2 has a factor in common with 12, not 3 because 3 has a factor in common with 12, not 4 because 4 has a factor in common in 12, but 5 because 5 has no factor in common with 12, not 6, but 7, not 8, not 9, not 10, but 11. So these are all equal to Z12. And if we make a complete table, then here are the numbers: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 0. And what is the order? Well, 12 has order, 1 has order 12. 0, we don't talk about the order of the identity. I mean, the order of the identity element is 1 because you raise it to the first power, you get the identity element. Remember, the formula is n, if this is k, it's n 12 over the GCD of 12 and k. So here we would have 6, here we would have 4, here we would have 3, here we would have 12, here we would have 2, here we would have 12, here we would have 3. Let's just check that because the greatest common divisor of 12 and 8 is 4, and 12 over 4 is 3, 8, 16, and 24. This is 8, whoops, but of course 16 is just same as 4. 9, the greatest common divisor is 3, so we have 12 over 3 is 4. 10, the greatest common divisor of 10 and 12 is 2, so we should have 6. 11, we get 12. So these are the orders of the elements in Z12. And you notice they're all divisors of 12, and that's also a consequence of the fact that the order is n over d, because n over d is a divisor of n.